Okay, welcome guys. Today we're going to take a look at the differences between Bayesian versus classical statistics. And to do an example of this, I actually used this example in my intro statistics class this week, and I thought it would make a good example of how you can use Bayesian statistics for you guys in my upper level class. So let's take a look. So last year, and I do this most years, I take data from my students, and last year 47 students took statistics with me, and of those 29 were born in Virginia. And so that's a sample, and I think it's probably pretty representative of Hampton-Sydney students. I mean, the people who take statistics are there's no reason why there would be more Virginia students in there than other states. So I'm going to assume that there's no bias in this sample, and so I'm ready to go ahead and try to do some statistical inference to find out what is the true proportion of all Hampton-Sydney students who are born in Virginia. So to get us started doing this the Bayesian way, you need the likelihood function for the proportion, starting with a model. And the model we're going to use is a simple binomial distribution model, which makes sense because if you have 47 students, each one either is or is not born in Virginia. So it's like binary outcomes, 47 independent trials. Binomial distribution is the right distribution for this. So we're going to use that model, and then if that's our model, then the likelihood function, you just write down the probability mass function for a binomial distribution with 29 successes, and then if you have 47 total, that means you would have had 18 quote-unquote failures. And here, remember, we're thinking of a failure as someone who was not born in Virginia. And so there we go. So that's the probability mass function with the numbers that we got plugged in, and now we just think of it as a function of p and call it the likelihood function. So that's the likelihood function for p given that x was equal to 29. So I asked you to find that. And then the second question I said is, so also what is the posterior distribution for p if we start with a uniform prior, so uniformly distributed between 0 and 1, which basically just means if we start with no prior knowledge about what p would be, we're completely uncertain. It can be anything from 0 to 1. And if I start with that, then what I do is I, as always in Bayesian statistics, take your prior times your likelihood, and since the prior is uniform 0, 1, it's just flat, right? It's just a constant function always equal to 1. So it doesn't do anything when I multiply it times the likelihood. So my posterior distribution ends up basically being the exact same thing, except for one important difference. The constant in front of the likelihood function is that 47 choose 29 number that you get from the binomial distribution. But when you think of this as a probability distribution for p now, then that's not the right constant so that the probability distribution has the right integral, right? The integral of the probability distribution should be 1, and it turns out that's not even close to right. So what you need to do is you need to find the right constant to do that job. And so the way you do that is you take the important stuff, the stuff without the constant, and you just integrate it to see how big the integral is. And actually the integral here is really, really small. It's a tiny, tiny number. It's 1 over some 219 trillion odd stuff. And so then when you divide by a really tiny fraction, you get a really big constant. You just get the reciprocal of that, which is this giant number. And then the stuff that's important is the p to the 29th and the 1 minus p to the 18th. Let me show you what that looks like graphically. So I pull up Desmos here. This is an example of a beta distribution graph. So a beta distribution for, this time I'm using the letter x instead of p, but that's just because that's what Desmos expects. And I've got my parameters a and b instead of alpha and beta. And then this is the constant c that will work. And I'm starting with alpha and beta equal to 1. And what that looks like is just a flat, it's just the uniform distribution. So the beta distribution when alpha is 1 and beta is 1 is just the uniform distribution on 0 to 1. And now let's change this. So let's bump the alpha all the way up to 30, which is the right alpha for ours, because in a beta distribution, the alpha is whatever this number is plus 1. So 30 would be our alpha, and then the beta would be 19 because it's 18 plus 1. So we'll bump this up to 19, and there we go, 19. And well, you can't see anything, right? Because this is so tiny. When you do little numbers, x is somewhere between 0 and 1, you raise them to big powers, you get really small answers. So this is really small. So we need to make the constant really big. So let me slide this up as high as it'll go. Right now it's only going up to 100 and it's still not enough to make this visible. You need to go a lot higher than that. And that's where I used Wolfram Alpha to calculate this integral and see what it needed to be. And it turned out you needed to have something really, really huge as your constant up front. So you need this monstrosity. So let me copy and paste this ginormous number in Desmos and see if it can handle it. So if that's the constant in front, there you go. That works. So now we can see our beta distribution. So we needed a huge constant to balance out these powers of a really tiny x. Okay, so now you can see the distribution. You can see what our data is telling us about the proportion of students who were born in Virginia. The posterior distribution is saying, well, it's probably around 0.6, maybe 0.7, might even be as high as 0.8, but it's probably not much higher than that, right? The probability distribution for this stuff is really low. So it's probably not higher than 0.8, and it's also probably not lower than 0.4. So we can be pretty confident that the percent of Hampton-Sydney students who were born in Virginia, if you get your hands on all of the Hampton-Sydney students and find out how many were born in Virginia, that number is probably between about 0.4 and 0.8. Awesome. So that's how you use a posterior distribution. And I asked a question about using the posterior distribution over here. I asked, okay, so what is the probability, according to the posterior distribution, that more than half of the students at Hampton-Sydney were born in Virginia? And so I suggest using Wolfram Alpha to do the integral. But what you do is you integrate the posterior distribution over the region that you care about. And let me come back to my graph here. And so I've got this graph, and I'm going to do the same thing. I'm going to visually show you what that integral looks like. So I want all the things where the y value is less than this graph. And let's copy that. So that's it. So I want the area under the curve, and that's kind of an ugly color, but I don't know. It'll take me too long to figure out how to switch it. So we're going to go with that ugly color. And then I don't actually want this all the way from 0 all the way up to 1. I only want the area under the curve from 0.5 up to 1. So we just want to start the integral here at 0.5 and then keep integrating. So I want to know what's the probability I land in this part of the distribution. And as you can see, it's going to be a pretty big percentage because I'm just cutting off this little tail on the left. And so you just integrate from 0.5 all the way up to 1. When I did that using Wolfram Alpha, I got a 94.3% chance that you get a result bigger than 0.5. And I typed this in wrong. That should be the probability subscript Hampton-Sydney. So a little LaTeX error. Anyway, but there we go. The probability that the proportion of Hampton-Sydney students who were born in Virginia is greater than 0.5 is something we can actually calculate in Bayesian statistics. And if you think about this, this is something you never do in classical statistics. In fact, it's something you never really even talk about, is what's the probability your parameter of interest is in a certain region. You really just kind of avoid that entirely. So like you do this weird thing called a hypothesis test in classical statistics. And so I walk you through the hypothesis test in here in problem 3, and let's see how that works out. So the null hypothesis, if you want to know if more than half of Hampton-Sydney students were born in Virginia, you'd start with a null hypothesis saying, well, maybe it is half. Okay, that's a specific number that we can use as a starting point for our calculation. And then maybe it's not half. That would be an alternative hypothesis. And so if I have no prior knowledge, then I wouldn't know which side it's on, so I should do a two-sided alternative hypothesis. And then I go and get my data from my class, 29 out of 47 students. That's the p-hat. The null hypothesis value is p0, so 0.5. And then I put in all those numbers down here, and I end up getting this. I get p0 was 0.5, so multiply that times 1 minus p0, you get 0.25, and then the sample size is 47. Crunch the numbers, you get a z-value, 1.6. So on a bell curve, which is the model we're using in classical statistics, right, we're approximating a binomial distribution, saying, well, it's approximately normal because we have this 47 is big enough sample size, right? It's been a while since we've done that, but yeah, that's what we're doing here. So on a bell curve, we can ask, so what's the probability of getting a result as extreme or more than this 1.6 z-value that we got? And you can easily do that using R or just using like a probability distributions app. And when I checked the number, I got 11%. So there's an 11% chance of seeing a result this extreme if the null hypothesis is true. And when things happen 11% of the time, that's not that unusual. That's the kind of thing that really could just happen by random chance. And so it's not low enough to be statistically significant, right? Things don't even start to be significant until around 5%. So this is not significant, so we can't reject the null hypothesis. So basically, if we're doing classical statistics, at this point we would just kind of shrug our shoulders and say, I don't know, like the test is inconclusive. We can't tell if more than half of Hampton-Sydney students were born in Virginia. And that's much less than we're getting out of the Bayesian statistics approach. In the Bayesian statistics approach, we are actually getting a whole posterior distribution that tells us basically everything we know right now about the proportion of Hampton-Sydney students that were born in Virginia is under this curve. And so you can say things pretty confidently that, like, oh yeah, well, in this posterior distribution, it's a 94% chance that we're going to be above 50%. So we can be 94% sure that the percentage of Hampton-Sydney students who are born in Virginia is above 50%. So how is this so powerful? Well, Bayesian statistics gives you a lot of power, but you have to make a really big assumption at the beginning to get started, and that is your prior distribution. You have to assume that the data has a prior distribution. Now, we actually started with a pretty weak prior distribution, so this is not a big assumption. Our prior was just the uniform prior, which basically was like, I don't know, it could be anything. And already we're getting a lot more out of the Bayesian statistics. The other problem with Bayesian statistics is it is a little bit more difficult. You really need some integration, which is another big reason why we don't teach this at the introductory level. Okay, so that's how Bayesian statistics works. I think it's really nice. Now let's move on. On the next page, well, actually, before we do that, I had one more question that I asked. I said both the p-value that we just calculated and also the Bayesian calculation that we did in problem 2 are examples of what are called conditional probabilities, right? We have a probability of something given something else, or the notation the statisticians use is the probability of A given B. And so I wanted you to just think for a second about what were the two conditions, like what was the given and what was the thing we were trying to find the probability of in problem 2, and what was the given and the thing we were trying to find the probability of in problem 3. So the Bayesian probability that I wanted to know was what was the probability of the percent of Hampton-Sydney students who were born in Virginia being greater than 50%. So the P subscript HSC or HS is greater than 0.5, given the results that we got, given that in my sample, 29 out of the 47 students were born in Virginia. So that's a conditional probability. So always when you're doing a Bayesian statistics calculation, you're calculating a conditional probability, conditional on the sample data that you had. And that's a really nice way to do statistics. The way we do it when we do classical hypothesis testing is not so nice at all. It's actually very confusing, and this is the hard part when you're doing hypothesis testing, is really wrapping your head around what it is you've actually calculated when you calculate a p-value. Remember, a p-value is the probability of getting results at least as extreme as what you got if the null hypothesis is true. And so that's this conditional probability, right? The A is the probability, is the event that you got results at least as extreme as what actually happened. So it's like the parts of the bell curve that would have z-values more than 1.6 away from the middle, given that the null hypothesis is true, given that the middle is where you thought it should be if the null hypothesis is true. So our p-value is 11%, and then we had to go through the whole process of thinking, is that low enough to be significant? If it is significant, what does that mean, right? It means that it's probably not a random fluke what we're seeing, which means we can reject the null hypothesis. But in this case, it's not significant because it's not low enough to be confident it's not just a random fluke. So we can't reject the null hypothesis. I really like the interpretation of the Bayesian statistics better. It's way simpler. It's just 94.3% chance that the percentage we care about is over 50%. Nice, simple. So once you can get into Bayesian statistics, oftentimes the answers you get are much clearer. Okay, the next thing I had you guys look at was what are called credible intervals. These are like a Bayesian version of confidence intervals. They're very similar to confidence intervals, that you just approach them with a different approach. Confidence intervals, you have a nice simple formula, you plug in your numbers, you're done. Credible intervals, you really need to work with those posterior distributions to sort of squeeze out the data. And there's actually more than one way to do credible intervals, but I'm just going to focus today on the simplest version, where if you want a 95% credible interval, then you just cut off the 5% that you don't want, usually 2.5% on the left tail and 2.5% on the right tail. So you just need to find the quantiles in that beta distribution. The first quantile is at the 2.5% level, and then the next quantile is at the 97.5% level, so that between those two quantiles you get 95% chance of getting what you want. So let me go back to Desmos. I've got this picture here. I actually made a different picture where this is the same beta distribution, and here I show the two parts, the two tails that I don't want, right? So I want to find 5% on the left tail, and 2.5% on the left tail and 2.5% on the right tail, so that this middle part, the white part in the middle, is 95% of the posterior distribution. And the place where that happens here, according to R, let's go back here, according to R, the Q beta command, the quantile for the beta distribution with parameters 30 and 19 at the 2.5% level is 47.435%, and the quantile at the 97.5 is 74.23%. So I can be 95% sure that the percent of Hampton-Sydney students born in Virginia is between these two numbers. All right, that's it. That's how the credible interval works. The confidence interval formula is also a good tool. I'm not saying that those classical tools are bad. I definitely think hypothesis testing is more convoluted. Confidence intervals are a little easier to work with. And so if you use this formula to make a confidence interval, what's really interesting is you actually get very similar results to the credible interval. And it actually is easier to use this formula, definitely, than pulling out a beta distribution. So when I use the formula, I got a 95% confidence interval for the proportion of Hampton-Sydney students born in Virginia is between these two numbers here. Awesome. Okay, so credible intervals and confidence intervals are similar, but they come from very different tools. This is based on the normal distribution model for a binomial distribution, normal distribution approximation. This is based on using the likelihood function and a prior distribution to make a posterior distribution. Also, I should say the credible interval completely depends on what your posterior was. If somebody else thought they had some prior knowledge and used a different prior distribution than I did, then they would get a different posterior distribution, and so they would get different numbers here, which can be a really good thing if you kind of, like, if you've done this every year, if you've collected data from your students, and each year you just update your old prior and make a new posterior based on that, and then the next year you take your posterior distribution from the last year and then update it again with the new data and make a new posterior. You can just keep updating as you go along, which is a nice feature of Bayesian statistics too. All right, so that's how all of that works. As always, please let me know if you have any questions, and we'll take a look next time. Probably we'll do some inference about quantitative data using normal distribution, and I'll try to post some problems similar to this one, maybe with some other distributions too. All right, take care.